Assalamu alaikum and hello everyone. The other day, while I was surfing YouTube as always, I came across this video by Blender Path, and it is Simulation in Blender 3.6 Geometry Nodes tutorial. So the thing with this video is that he is trying to simulate this effect. Particles rotating around a center, apparently, and with some physics in it. However, he is using vector math to predict the direction of the points of the particles to achieve the rotation. And there is another approach for the same problem. So the problem of simulating the rotation has two solutions. One is to predict using vector math estimations, and the other is to use the rotation matrix transformation to transform the point from one position to another. Since Blender Path has a whole video describing the vector math technique and how it works, I am going to focus on the other technique, which is applying the rotation matrix on the points to move them from one position to another to get a perfect rotation. Now, the other technique, the rotation technique, the applying of the matrix will solve a lot of problems with this technique. This technique has some inaccuracies, and the rotation matrix will remove that inaccuracies and get rid of them. So for example, when he runs it, the points tries to repel from the center. They are trying to go away from the center. And that effect is because of the inaccuracies in the estimation. So the rotation matrix will get rid of that inaccuracies, and we will get a perfect rotation achieved. So the thing that you see on the screen at the moment is my implementation of the same simulation, at least in the beginning, the first part of the simulation, which is rotating the points around the center. And if I hit play, as you can see, the particles are not repelling away from the center. Actually, they stay in the center, they rotate as expected, and if I move the center here, the whole system rotates around the center again. So it's less work, it's more accurate, but it might not be very pleasant to the eye. So the main thing about this approach is it's visually pleasant, because this is how hurricanes are formed. They are not just making particles stick to the center, they're just throwing them away. But if you want to have another, let's say you want to simulate a honey, and you're trying to mix that honey with a spoon or something, you're blending it. So you need the points to be stick to the middle, because that's how honey and dense liquids behaves. Particles tend to stick to the middle, so basically they are sticky. So to simulate that, you cannot really simulate it with the Blender Path vector math estimation based prediction. So for that we need some approach that has a perfect, that provides at least a perfect angular momentum or a perfect angular rotation, and that's why I am making this video. So in this video we will be creating the geometry nodes of the plane, same as we're doing with the same as Blender Path did in the first phase of his video, and then instead of making it with vector math based estimation, we're going to make it with rotation matrix, or applying the rotation matrix to the point. Let me show you what the vector math estimation does behind the scenes. So for that, let's reduce the count to 0.1. That's perfect. I already went ahead and put a circle in the middle to demonstrate what I'm going to say. So in the vector math approach, or what it does really behind the scenes, is that it's trying to get a direction of where the point will be moving. So in this case, the point will be moving along this direction. It does that by getting the point vector from the center, and then by doing the cross product with the up vector, and then we get this vector. So we get the direction of the point. And since we know the direction now, let's move the point along this direction in a smaller step. So for example, let's make the point move up to here, this point over here. Now we have the point here. However, notice that the movement was linear, okay? And this is a circle, and this is a line. So we move it here. If we repeat the process again and again and again, apparently we start accumulating the error between the position of the point and where it should be, its orbit. So, for example, when the point is here, we will have this much error. And that's why points repels from the center in the vector math approach, or the vector math based estimation. The rotation matrix does manipulate the space in another way. So it's not like vector math, it does it in a different way. Instead of trying to move the point along a direction, it is moving the point based on the angle. So we must give it an angle over here. Let's say we want to give it this angle, and the matrix transformation will be applied to this point and move it to here. So since this point is comprised really of x and y, the matrix multiplication will transform the x and y values to this new x dot, let's say, and y dot. So how does it really do that? And if you want to know really how it does that behind the scene, I highly recommend you watch Freya's Holma video on rotation matrices. And in that video, really, she explains why the rotation matrix behaves this way, why the rotation matrix takes a point and transforms it to another place. I highly recommend you watch her video before coming to this video. I will put it in the description below as well. But long story short, what we need to know for this video or for this implementation is that we need to know that multiplying the x and y values at this point by the rotation matrix, let's call it R, will move the point along its orbit. So we just need to multiply the x and y of the point by the rotation matrix. And how to create the rotation matrix? If we go back to Wikipedia, we can see that it's cosine, negative sine, sine, cosine. As you can see, we have, if I go here, let's get with value, and then we have value, let's go with sine. So we have the sine, we can also have cosine, whatever, whatever, whatever. So this is a math node. So geometry nodes can do it for us. It can get the cosine and sine. And what we need is to multiply the x and y by the rotation matrix, which is gotten through geometry nodes. So I went ahead and created an empty Blender file, deleted the stuff, and in this file we will be doing our simulation. First of all, let's start by adding a plane. Scale it, and let's add the plane first. Scale it, and then Control A to apply all transforms, because I mostly forgot to do it most of the time. And then let's add geometry nodes to it. Given the input, it manipulates the geometry, and then it outputs the geometry back to the viewport, to the rendering screen. So let's manipulate it to show an example. Let's distribute points, and now we are transforming the geometry into multiple points, and then we are showing these points in the output in the screen. And for this demonstration, we don't really need this much, we just need 1 or 2. 0.1 seems good. We can start actually rotating the point. We can take this point, apply the transformation matrix on it, the rotation matrix on it. It will be rotated. However, it will be rotated with respect to the Blender center, which is the origin of everything, the one and the only. So to avoid that, we need to create an object. So when we move that object, the points will be moved, rotated around that object. It will be orbiting an object, not just the center of the nothing, center of void. So let's create an object so we can have more fun with it. Can be anything, but let's go with UV sphere or icosphere, it doesn't really matter. And back to the geometry nodes, let's bring that object to the geometry nodes panel. So by drawing the object, we can just get its data. What we need right now really is to simulate the points, to move the points. It's so small, let's increase radius. Set point face radius. Let's increase it by a bit. This one is good for the demonstration purposes. So we have points. We have the object, this object, in the geometry nodes of the points. What we need right now is simulate. Each frame we will be calling a simulation function. We will be repeating some set of code in that zone, and that zone is called the simulation zone. Let's get the simulation zone here, connect it, and right now it will not do anything. So to demonstrate what it does, let's set position. We are going to set the position of the points, but instead of setting position directly, we are just going to offset it by a bit. Let's say we are offsetting it by this one, this much. Just hit play, and as you can see, points are moving toward that direction. Offset it every time in each frame by this amount. make it 0, and let's restart the animation because we want it from 0. Now, what we are going to do, how are we going to rotate the points with respect to the center? And for that, we first of all need the point, and we need the position of the point, the vector of the point from the center, because we want to rotate it with respect to the center. So, and to do that, it's just the point location minus the center location. Since subtracting a point from a point will give us a vector forwarded toward the first argument or the first operand. First of all, we need to start by getting the position of the center and the position of each point. So not points, my bad. We have to write positions here. I'm looking for positions, we're getting position. This position node will represent each of these nodes individually at each time. So this is not just a single value of a single node, this is all values of all nodes. And what we need now is to subtract the position of each point with the location of the center, because we want to move the points or rotate the points with respect to the center. So we need to transform the points from the global space to the icosphere space. And we can do that with subtract node. In Blender, we want to subtract the position from the icosphere, and let's name this P for now. And since we want to get the x and y of P, because we want to apply the rotation matrix on x and y based on these equations in Wikipedia, which x prime is equal to the new position and y prime is equal to the new position. So we need to subtract, we need to separate the point into its individual components. We can do that with the separate node. Separate x, y, z. Let's move this a bit to the back, and then we continue from here. Now, to apply these equations over here, we need to get the cosine of theta and sine of theta. Now, luckily enough, Blender have a sine and cosine nodes, and we also can have a value node. Let's make this theta for now, and then put it in a value. 0.1 would be good. And we have sine, we have the cosine. Now we have all the requirements for applying this equation. We have the x, we have the cosine, we have the sine, and we have the y. We can get the new x prime and y prime. Make sure that the sine and cosine are accepting radians. So this node over here, this node must be in radians. What I need to do now is to apply this equation in Blender using geometry nodes. So we have x, we want to multiply sine with cosine actually, because I want to do x prime now, and then let's check multiplication again with y sine, and we do subtraction. Now this will be our x prime. We need to combine the nodes, combine x, y, z. Now this will be our x prime. This will be our new position node. Move it to the back, and we need to do the same to the y prime. We need to get the y prime, and for that we also need to follow this equation: x sine theta, y cosine theta. So x multiply sine theta, y multiply cosine theta. Here we add addition between this node and this node, and then we make this the y prime. Let's test it out by putting it in the position, hit space, and as we can see, we have a four rotating particles or points around the center, this one, and they are moving seamlessly in rotation. So perfect rotation, they're not moving backwards. Finally, to put the cherry on top, we need to care about one thing. If we run play and let's move the center here. As you can see, the points are moving in the wrong direction. They shouldn't be moving leftwards if the center is moving rightwards. And that is mainly because we apply transformations. So we got the vector to the point, we transformed the point, and then we didn't put the point back to its respective place, which is in the global space. So that's what we need to do at the moment. And that can be done actually by adding the output. So since we transform the point to the icosphere space by subtracting the point minus c, we can just return the point back to its original place by just adding c. So that's what we are going to do. If I turn back the timeline, delete nodes, and here I'm just gonna add and add, and here we will only have, actually let me just drag the icosphere here, put the location here, and then instead of using the xy prime directly, we gonna use the xy prime transferred to the center of the world. So now if I hit, let's go back to this one. So if I hit space, you will see the points rotating all rotating around the center, which is the sphere, which is correct. They are orbiting the sphere. Now the problem with this one, the last problem to solve with this one, is that all points are moving with the same velocity, and that is not. This is not appealing. Should not be happening. It should be happening with this implementation, but we should try to make it closer points moving faster than further points. And to do this trick is quite simple, simpler than you think. We just need to change the theta, this one, based on the distance of the point from the center, from the sphere. So let's go back again, delete the annotations. So let's say we have the points moving. Now if I, as you can see, the way that I change the value, the theta, the point's speed will decrease or increase. Now we want to change the value theta by how much distance the points are from the center of the world. The center of their world at the moment is icosphere. So to do that, we just need to get this one. We need the length of this one. Now the length will allow us to get the distance between the point and the icosphere. So after getting the length, what can we do with the length? We need to do some kind of a mathematical trick. Given the length, we want to determine the speed. So basically, the shorter the length, the higher the speed, the larger the length, the lower the speed. And we can do that by 1 over x, okay, or 1 over the length. 1 over the length give us an inverse equation, or the inverse function. When the length is closer to 0, the 1 will be large, very large, so very fast rotating. And when the length is large, so let's say the length is 10, then the output of this equation will be 0.1, something like that. So let's delete it and go back here, and then we're gonna divide it. We're gonna divide, but we want the length to be in the denominator. This value over here will be our theta, not this value. So let's put 0.1, since this is the initial speed, the initial rotation, angular rotation. And if we hit space at the moment, they are moving in different speeds, but we cannot see that because this is very slow. So if I increase the theta, you can say that this point is moving faster than the outer points, these points, because of how close they are to the center, to the origin. Now let's move this point a bit. As you can see, it is affecting the flow eventually. Let's increase the point, make sure that all transforms are applied, reduce the radius, a bit, increase the points, reduce radius. I think this is good. If I do simulate, start, as you can see, they are rotating around the center, and we see this pleasing visual effect. I like the shape of how It looks like something like a lizard in a womb. Still an embryo lizard. And that's it for this video. Thank you for watching. I hope you learned something. Salam.